So good morning, everyone. Welcome to the second session of the FDP on day 8. We have Dr. Vairi Vignesh sir, who has been with us also on day 5, a young dynamic professional with high research-oriented skills. His His research areas include solid-state processing, solid-state welding, surface engineering, corrosion science and technology, and tribology. He's currently working as professor at Amrita School of Engineering, Coimbatore. Sir, we welcome you to the session, sir, on behalf of MLR Institute of Technology, the HOD and Principal, Dr. K. Srinivas Rao, sir. Sir, you are there? I'm sorry. Sir, am I audible?
Yes, ma'am.
Yeah.
I could hear you.
Welcome to the session, sir.
Yes, please.
Yes.
So, good afternoon, everyone. So, I am Dr. R. Vaira Vignesh, serving as Assistant Professor in the Department of Mechanical Engineering, Amrita School of Engineering, Amrita Vishwavidyapitham, Coimbatore. In today's session, I'll be discussing on the influence of nano phase alumina and the corrosion behavior of magnesium alloy AZ91D. So, here'll be a brief introduction about myself. I did my BE from Karpam College of Engineering. Then, by the year 2015, I have joined for PhD at Amrita Vishwavidyapitham. I have worked as research fellow in DST-funded projects. And by the year 2019, I have successfully defended my PhD and joined here at Amrita as assistant professor. I have 30 plus publications, 20 plus conference publications, and 4 book chapters to my credit. So before starting the contents, I could briefly elaborate the research facilities in our lab. So I am part of 2 labs at Amrita. One is friction stir welding lab. In this lab, we do work on friction stir processing, friction stir welding, and friction stir spot welding of materials. We work on aluminum alloys, magnesium alloys preferably. And coming towards the facilities at Amrita Vishwavidyapitham, we have friction stir welding and processing setup, immersion corrosion setup with thermostatic bath, a continuous casting setup, 4 high rolling mill, foil rolling mill, vacuum brazing furnace, high vacuum brazing furnace, high frequency induction furnace, and multi-purpose heat treatment furnace. These facilities are established under the assistance of Department of Space, DST, ISRO, and Amrita. So here's the outline of my presentation today. So we'll start the session with a basic introduction to corrosion testing methods. Then we'll just discuss on electrochemical corrosion analysis of metallic specimens, followed by friction stir processing, a solid state processing technique for the fabrication of surface composites. Then the outcomes of the research, that is nano phase alumina reinforced with magnesium alloy, magnesium alloy AZ91D reinforced with nano phase alumina. Corrosion testing methods. So generally speaking about corrosion is always defined as a deterioration process of a material as it interacts with the environment. But I would like to differ from this definition. Why? Because corrosion is a process that helps materials to thrive in their native stable state. In the right side, we could see 3 images where we could observe the states of metal ore in the native form, and during this extraction process we supply an enormous amount of heat into it, thereby increasing the activity of the material. In its pure form, the metal's activity is so much higher. Okay, and since metals are not ready to be in the native active state, they just start to corrode and then they come back to their ore state. So that process is defined as corrosion. So when we want to find the secrets of universe, obviously we have to think in terms of energy, frequency, and vibration, as said by Nikola Tesla. So corrosion is not a deterioration process. It is a process that helps material to thrive in their native state, native stable state. And coming towards the physical properties of materials, they too influence corrosion. The physical properties, chemical properties, and the metallurgical factors. Let's say it is going to be phase fraction or the dispersion of phases in the matrix and the dispersion fraction, how they are dispersed, whether they are homogeneous or heterogeneous, that also influences corrosion. And coming towards the environment influences the corrosion rate of materials to a great extent. For example, local environments, maybe some sort of dust particles that is present on the metal surface will also contribute to corrosion through differential aeration methods. And if it is an aqueous medium, let's say it is going to be some water or seawater based or some fluid based, that will also influence corrosion rate of the materials. Coming towards stresses that is present in the material, and if the material is subjected to stresses in the corrosion environment, that will also enhance the corrosion rate of the materials in most cases. And the microbes, the flow factors like the flowability of the viscous medium over the surface of the material also causes corrosion to a great extent. So there are many factors that influence the corrosion rate of the materials. So we have many methodologies to test or to analyze the corrosion phenomenon that is taking place in the material. So that involves designing, planning, and preparation of corrosion tests for the specimens. That includes statistical approach and design of experimental approach. Generally speaking, always corrosion testing methods relies with simulated service corrosion testing environments or laboratory corrosion testing environments. In simulated service corrosion testing, what we do is we just take the specimen, we just place the specimen in the respective environment, and then we evaluate the corrosion characteristics of the material. But in case of laboratory corrosion testing, we just do them by mimicking the environment. Let's say, for example, if you want to test the material's capability in a marine environment, if it is a simulated surface corrosion testing test, we just take the specimen towards the marine area itself. For example, a seashore, we just do the corrosion testing there. We just keep the specimen there hanged for few days or few months or few years, then we just analyze the corrosion phenomenon. But in case if it is going to be a laboratory based corrosion testing, we just create a solution that mimics seawater. For example, 3.5% of sodium chloride is always considered as simulated seawater. Okay, so that can be used for laboratory corrosion testing methods. So in this, widely people use electrochemical methods, immersion testing methods, autoclave testing methods, and cabinet testing methods, of which immersion testing methods are always find a good place in testing methodology. Why? Because in immersion, we'll be able to analyze the corrosion products too. So that's a great advantage of going with this immersion corrosion testing. But the limitation of this immersion corrosion testing is the time consumption. Okay. But when we have to test the corrosion rate of materials for an extended period of time, then immersion testing will not work out to a great extent. So for that cases, we have to move towards electrochemical methods of testing or evaluating the corrosion phenomenon that is taking place in the material. We'll just see the basics of electrochemical corrosion test with respect to potentiodynamic polarization in detail first, then we'll go ahead with the results of our study. Electrochemical corrosion test. So an electrochemical cell, we'll start with basics. So electrochemical cell is one that is formed by connecting two electroconductive metal rods in a solution. So that solution is always called as an electrolyte because it involves electrochemical reactions. And the electrode which loses electron is termed as an anode, or the region or the electrode that is subjected to oxidation reaction is called as an anode. Similarly, the electrode that is subjected to reduction reaction or where electron gain takes place, that is called as cathode. The liberation of electrons and the flow of current depends on the activity of materials, and based on this activity, elements are arranged in sequence. That sequence is termed as galvanic series. So the galvanic series is prepared by just performing experiments with respect to standard hydrogen electrode. So we just consider that the standard hydrogen electrodes potential is 0 volt, and then we have made this come up with this galvanic series. So the leftmost elements are highly active. For example, magnesium is highly active with respect to aluminum, and it is more active with respect to gold. Okay, and the rightmost element, let's say it's going to be platinum and ors, they are going to be most stable, or they exhibit cathodic nature. So the leftmost elements have anodic nature and rightmost elements have cathodic nature. If we just couple these two elements, obviously we'll end up with corrosion phenomenon. Okay, yeah. So what we do in polarization test is we just deliberately change the electrode potential of the specimen from the equilibrium value to the desired value. So that is done with respect to more negative and more positive corrosion potential. For example, in the first instance, what we do is we forcibly make the electrode to behave as cathode by polarizing the specimen towards more negative potential. And after that, we just bring back the potential of the specimen towards its current form. Then we forcibly make the electrode to behave as an anode by polarizing the specimen towards more positive potential. Okay, and this is done using a potentiostat in electrochemical workstation. So this potentiodynamic polarization method will give us the data on the existence of limiting current in the material, and it will help us in investigating the corrosion mechanism that is present or that is in the characteristic of the material that we have chosen. And we could just analyze the corrosion mechanism takes place through activation or concentration based kinetics. So in activation based kinetics, the reaction sequence at metal electrolyte interface, the corrosion rate is controlled by the reaction sequence at the metal electrolyte interface. And in concentration kinetics, the reaction rate or reaction is controlled by the diffusion of electrolyte, diffusion in the electrolyte. So this happens in weak or eroded salt solution. Okay, and activation based kinetic takes place in concentrated solutions preferably. And coming towards the working methodology of this potentiodynamic polarization method, what we do is we just take the working electrode, we just place that inside the container that has the electrolyte solution. This electrolyte solution, if we want to check for materials that has to be in marine environments, we generally use 3.5% of NaCl solution, that is mimicking the seawater environment. And the reference electrode is the one that is used to measure the working electrode potential of the electrochemical cell. So this has a constant electrochemical potential as long as no current flows through it. So generally we go ahead with standard calomel electrode or silver chloride electrode for reference electrode. And counter electrode is preferentially inert conductor that could be like a platinum or a graphite based one. And coming towards a potentiostat, as we have discussed already, the potentiostat is an equipment that controls the voltage difference between a working electrode, that is our specimen, and the reference electrode. So this is carried out by implementing or injecting the current into the cell through the counter electrode. Then the potentiostat measures the current flow between the working electrode and the counter electrode. From this, we can obtain the corrosion current of the material. So we can obviously say that the controlled variable is the cell potential and the measured quantity is the cell current. So based on the value of cell current, we can interpolate the corrosion rate of the specimens. So let us take a simple case study where I'll just discuss how to calculate the values of corrosion potential and corrosion rate based on this potentiodynamic polarization. So in this, we have a specimen as working electrode, standard calomel electrode as reference electrode, and platinum wire as a counter electrode. The exposure area is 1 mm square, and the electrolyte solution was simulated seawater, that is 3.5% of sodium chloride dissolved in deionized water at room temperatures. The temperatures can be varied. That is also one of the parameters that influence the corrosion rate of the materials. Then what we have to do is we have to establish open circuit potential for 60 minutes. That is, we have to leave the setup for 60 minutes completely and we have to measure only the potential that is coming out of the working electrode. That is the potential that is set up between the working electrode and the reference electrode. That is what we have to measure. So once this open circuit potential becomes stabilized, then we can go ahead for potential dynamic polarization scans. So this OCP potential will be used as the reference potential for anodic and cathodic polarization. The specimens will be subjected to polarization at a scan rate of 5 millivolt per second in the potential range of minus 1.5 volt to minus 0.5 volt. And this potential range differs from material to material. For example, if we take magnesium based alloys, obviously we have to go for more negative potential. Why? Because magnesium is itself has more negative characteristics with respect to cathodic anodic behavior. Okay, yeah, fine. And this is how the potential dynamic polarization graph looks like. So it will just look like a V graph over here. The blue colored one is zoomed in for our convenience. So this could be done using MATLAB or some software that is available, readily available in the internet sources. So this was done using a MATLAB. So what we have done is we have to take the potential drop region where the potential is going to towards more, where the current is very, very minimal. So that is our reference potential. So that from that, within the range of plus or minus 20 millivolt, we have to draw slopes to the cathodic and anodic curves. So where these cathodic and anodic curves intercept, that point is going to be our corrosion current. And obviously this intersection point will correspond to potential. So that potential is termed as corrosion potential. So this process is called as extrapolation, because we just extrapolate the values to get ICAR and ECAR. So from this ICAR value, we can able to identify the corrosion rate of the specimens using the equation that is given over here, which is given by corrosion rate is equal to K into IE by A into rho, where K is constant representing the corrosion rate in terms of mm per year, I is the corrosion current, E dash is the equivalent weight of the corroding specimen given by the ratio of molecular weight to the number of electrons that is involved in the chemical reaction. For example, if we take aluminum, three electrons will be involved in this corrosion process. If we take magnesium, that is going to be just 2 electrons. So the E dash value depends on the molecular weight and the number of electrons that is taking part in the chemical reaction, and rho is the density of the material. Even this ICAR could be identified or found using the slope values, which is given by equation below. So ICAR, which is equal to beta A into beta C, where beta A and beta C is the slope of anodic curve and cathodic curve respectively, and RP is polarization resistance value. So even this formula can also be used to calculate ICAR, or just by drawing this slope, we can just directly correlate with ICAR and ECAR value as shown over here. So this is how we calculate corrosion rate and corrosion potential using potential dynamic polarization method. I hope we are clear about this concept. So with this, we'll just move towards our biodegradable implant concept. This is what I have explained already in our past class. Even if I just give a refreshing session of this biodegradable implants. Implants are materials that are engineered to interact with the biological systems, and these implants are utilized for hard tissue fractures. So these implants are utilized to substitute or support the functionalities of the damaged bone. So implant materials may be of polymeric, ceramic, or metallic types. The problem with polymeric types is their limited biocompatibility. And coming towards ceramic, they have limited machinability characteristics. We can go with alumina, silica, zirconia, or hydroxyapatite based ceramic materials for implant fabrication, but they have limited machinability characteristics. Coming towards metallic materials, conventionally people are using the stainless steel, chromium, tungsten, titanium, cobalt, chromium based alloys. But the problem with these conventional metallic systems is they are very high density, compressive yield strength, and Young's modulus than that of the human bone. For instance, we could see cobalt chromium alloys. The density of bone is 1.8 gram per cc, but cobalt chromium have density of around 8.86, and their compressive yield strength, which is for bone, it is around 130 megapascals, and for cobalt chromium, it is around 1714 megapascals. And Young's modulus, it is going to be 6 times higher than that of the bone in cobalt chromium alloys. And generally speaking, all these conventionally used metallic materials have very high density, very high compressive strength, and very high Young's modulus than that of the bone. So why it is not desirable is this undesirably high strength and Young's modulus creates tendency for the implant material to absorb the stresses that are normally transmitted to the specific area of the body. So that will result in reabsorption of the developing bone material. So that will deteriorate the bone density. So accretive process like the tendency for the implant material to absorb the stresses and deterioration of bone density will lead to loosening of the implant and will ultimately result in bone refracturing phenomenon. So this process is generally called as stress shielding effect. So this is prevalent in conventional metallic materials. So added to that, these materials are non-biodegradable in nature too. It means we have to do a secondary revision surgery after the bone heals completely. So that also has a huge impact on the wellness of the patient. And added to that, the corrosion and wear debris are non-biocompatible in nature. So this leads to accumulation of toxic ions within the bone region. So that leads to inflammatory osteolysis. So we should ensure that we have biocompatible corrosion and wear debris even when the implant is placed inside the human body for an extended period of time to avoid the inflammatory osteolysis condition. And added to that, if we ensure that the material that we use for implant is having a good strength and Young's modulus similar to that of bone, then we can avoid stress shielding effect. So people have been working on concepts of biodegradable implants for a very long time, and the concept of biodegradable implants is just illustrated over here. So we can just see the trend of regenerating bone towards, how the regenerating bone gains strength over a period of time. So it just starts from 0%, that is the fracture point, and 100% represents its complete recovered state. So it just takes a long time for recovery. So during this course, when we use a material with when we use an implant with conventional material, let's say it is going to be stainless steel or cobalt chromium or any other materials, that will have high strength with respect to the bone at all times. So that will result in stress shielding effect to a greater extent. So people started to work on this biodegradable concept. So in biodegradable implants, they will have gradual loss in mechanical and material strength during the degradation process that will be balanced by the increasing strength and stability of the newly forming bone. But the problem with the conventionally used or currently used biodegradable implant is that they just fail prematurely. So that is also not expected. Why? Because if they fail prematurely, they just uh, do not deliver the intended service period. So we have to develop a biodegradable implant that has an extended period of time towards bone healing period. Added to that, this biodegradable implant should support tissue regeneration and healing by dissolution, resorption, and formation of corrosion product that enhance osteoconductivity. So the key advantages for being a candidate bioimplant material for magnesium is its density, compressive yield strength, and Young's modulus. Why? Because the density is very similar to that of human cortical bone, the compressive yield strength, which is around 130 to 180 megapascal, and Young's modulus is also very similar. So these parameters make the magnesium as a key material for bioimplant applications. Added to that, if we use this magnesium alloys, that will result in marginal stress shielding effect than any other metallic materials. Added to that, magnesium has inherent ability to corrode in human physiological environment, which is rich in chloride ions. And magnesium ion is one of the cofactor of more than 325 enzymatic reactions that are required for proper functioning of internal organs. Besides, the serum magnesium levels is maintained by dynamic absorption and excretion equilibrium of magnesium ions. So this makes magnesium as one of the candidate material for biodegradable implants. However, there are limitations with magnesium. First is their HCP structure. The HCP structure limits the workability of magnesium alloys. And magnesium, as we have discussed already, it is a highly active metal that results in a high corrosion rate. And the low density of material results in high wear rate too. So in normal human body environment that is rich in chloride ions and it has a pH of 7.2 to 7.4, magnesium corrodes at a rate of 4 to 8 mm per year. So if we have such high corrosion rate, that will result in formation of hydrogen gases in the tissues, and that is a lethal phenomenon. So we have to do a process or prepare a composite to engineer the corrosion property of magnesium alloy so that we achieve a low corrosion rate. Generally, the bioimplants recommended corrosion rate is less than 0.5 mm per year. So if we are able to achieve this corrosion rate of less than 0.5 mm per year, that could be considered as an effective biodegradable implant. I hope we are clear until this concept. Then we have chosen magnesium alloy AZ91 as our base material in this study. So there are many studies that have shown light towards the potential use of magnesium alloys such as AZ31, AZ91, LAE442, AM60B, and WE43 towards bioimplant applications. And there are many studies that relates AZ91 with good biocompatibility, and even some animal study has also given good results in terms of implant applications, because this AZ91 has low in vitro corrosion rate uh, even when it is subjected to implantation studies in animals. Let's say it is going to be some guinea pigs and rats. So these things have made magnesium alloy AZ91 as a candidate material for biodegradable implant applications. So in this study, we have taken wrought alloy AZ91 of thickness 4 mm, whose composition shown over here as our base material, and then we have conducted experiments. So coming towards this magnesium alloy AZ91, it has two phases. One is alpha phase and beta phase. Alpha phase is the primary phase of the alloy, that is alpha magnesium, and beta phase is an intermetallic phase between magnesium and aluminum. So this phases influence all the properties of the materials. So for example, if these phases are present in a complete dispersed manner, then we'll have a normal good corrosion, good corrosion resistance. But in case if this beta phase is precipitated as a continuous network, we'll end up with high corrosion rate and intergranular corrosion too. Why? Because this alpha phase is more anodic than that of the beta phase. So that will result in a high corrosion rate in materials. So generally, when AZ91 is manufactured, we'll end up with continuous network of beta phase in the matrix material. So that has to be engineered to get a proper corrosion rate. Added to that, if this beta phase is present as a continuous network, we'll have limited tensile strength and hardness. But if it is completely dispersed as fragments within the matrix, then it will improve the tensile strength and hardness of the material too. And coming towards the cell adhesion and characteristics such as tribocorrosion, magnesium alloy, since its density is very low, it lacks in terms of wear. So it has high wear rate. So if we can able to make the composite or do a process to enable wear resistance, then it could be considered as an effective implant material too. So we'll just go towards the surface composite that is manufactured using Nano Phase aluminum oxide. So we have used friction stir processing, a solid state processing technique, to fabricate surface composite of AZ91D and Nano Phase aluminum. So in this process, what we have done is we have taken the workpiece, then we have made a groove of dimension 150 mm by 1 mm by 1 mm, and we have filled this groove with Nano Phase alumina particles. Then we have done a sealing pass. So sealing pass is done with an FSP tool without pin, okay, and that ensures that the nanophase particles or the reinforcements do not come out during the normal friction stir processing process. And this process is enabled by forcing the tool towards the workpiece under an axial load. This is rotated at some rotation speed and it is traversed on the workpiece. So this rotation and traverse cumulatively creates the frictional force that results in generation of frictional heat that plasticizes the material. So that plasticized material flows from one part to the other part based on the tool rotation. So that will give us an effective dispersion in reinforcements too. Added to that, there is mechanical fragmentation of beta phases in the matrix too. So we'll just see this microstructural evolution during friction stir processing in detail in the upcoming slides. So here I have shown the microstructure of the fabricated surface composite. In this, we have a stir zone in which we have a uniform dispersion of nano phase alumina in the plasticized matrix. This is this happened because this nano phase alumina aids in nucleation of magnesium grains during recrystallization, and this nano phase alumina restricted the growth of recrystallized magnesium grains. The stirring action of the tool, FSP tool, resulted in fragmentation and homogeneous dispersion of beta phase particles. So cumulatively, we have obtained refined grains, fragmented and homogeneously dispersed beta phase and nano phase alumina in the fabricated surface composite. So to confirm the presence of nano phase alumina, we have subjected the material to XRD analysis. So the XRD analysis confirms the presence of alpha phase, beta phase and nano phase alumina as shown over the graph over here. And coming towards the microstructural evolution phenomenon that happens in FSP is through static and dynamic recovery recrystallization that happens simultaneously in the material. So static recovery happens if the deformed material is subjected to high temperature. So if it is done, what happens is there will be annihilation of dislocation structures into a stable arrays, and these stable arrays form walls of dislocation. So these walls of dislocations are called as subgrain boundaries. So these subgrain boundaries act as a hindrance towards dislocation motion. So they result in the formation of subgrains. So obviously they improve the hardness and strength of the material too. Added to that, the second phase particles that we have added influences the low angle boundary. That is all because of this Zener drag effect. And this presence of second phase particles, that is nano phase alumina, reduces the growth of subgrains and promote dislocation preservation. Added to that, these second phase particles impede the dislocation motion with opposing shear stress, and this is significant if we have particle size of few nanometers. So obviously, since it is nano phase alumina that we have reinforced, as per the results of Humphrey and Hatterley, these particles will impede dislocation motion with opposing shear stress, which means we'll get somewhat better hardness and strength in the fabricated surface composite. And here's the process that happens when we have a static recovery. So when the material is subjected to strain, there will be formation of dislocations. These dislocations, if they are present in a continuous manner, they are called as dislocation tangles, as we could literally observe it from the image over here. Then if it is subjected to high temperature, there will be formation of cells and annihilation of dislocations within the cells, which will lead to formation of subgrains. And if the temperature is given for an extended period of time, that subgrains will subjected to growth also. So this does not happen in FSP, but it happens in some other processes if it is subject to some external heat treatment after friction stir processing. Okay, yeah, fine. So the dislocations in the deformed microstructure, if it reorganizes itself to form new set of strain-free grains, then it is called as static recrystallization. So we could identify the static recrystallization phenomenon that has happened to the material through high angle boundary. And added to that, we can say that if recrystallization happens, there will be strain-free grains from the strained grains. That is, the parent phase, which are strained grains, will develop into strain-free grains, which is the product phase. Added to that, the nucleation sites for the recrystallized grains include grain boundary, the shear band, and second phase particles. And the growth of recrystallized grains is interface controlled. Once we have more dispersion of second phase particles, obviously their growth of recrystallized grains will be greater. Since we have added Nano Phase alumina into it, obviously we'll end up with restricted growth in recrystallized grains. And if this happens simultaneously, the temperature and staining happens simultaneously, the material will be subjected to dynamic recovery and dynamic recrystallization. So this dynamic process exactly happens right beneath the FSP tool. So the rearrangement of annihilated dislocation structures into stable arrays occurs during deformation process itself. And the subgrain structure is typical to the static recovery process. So if we have continued application of strain, so that will result in introduction of new dislocation into the recrystallized grains. So they will form subgrains again, and this will inhibit their further growth. So this additional staining and formation of new nucleation states for recrystallization is called as series of recrystallization, which is also called as discontinuous dynamic recrystallization phenomenon. So this also happens in FSP. So this cumulatively adds up strength towards the microstructural evolution during friction stir processing of magnesium. To observe the dislocation, high resolution transmission electron microscopy, and the HR10 images of the fabricated composite is just shown over here. We can obviously see the bright regions is the alpha phase and the dark regions over here is the beta phase. So how we have confirmed this through ACA-ED pattern analysis. So we can just see the grain boundary and the dislocations that is present in the material, and we can see the triple point junction in the grains. We can see the subgrains and submicron beta phase particles. So we have confirmed the presence of the magnesium and the second phase particles, that is beta magnesium Mg17Al12 through ACAED pattern. The ACAED pattern is given as figure D over here. So indexing of that ACAED pattern will confirm us the material for us. And similarly speaking, we have done analysis over the nanophase particles too, and then we have confirmed the fine dispersion of nanophase alumina and beta phase inside the surface composite. So figure A, we can see the rings with distinct small spots and small spot making up the rings. So this is consistent with this despacing diffraction data of beta phase, and added to that, the insert in the figure B shows the SAED pattern of that particle. So when we have indexed that particle's SAED pattern, it was found that it is a nanophase alumina. So from this we can confirm that there is fine dispersion of beta phase and nanophase alumina inside the matrix, and there is formation of dislocation tangles and subgrains within the microstructure of the material. So we have a refined microstructure and confirm this ocean of beta phase particles in the surface composites too. And coming towards micro hardness, the base materials micro hardness was around 57.9 HV, and this was taken at load of 100 gram force, and the stir zone, which is the had 62 HV. So approximately there is 8% increase in the micro hardness of the material. So this hardness improvement is finally attributed to the presence of refined grains, fragmented and homogeneously dispersed beta phase and nanophase alumina. Coming towards the peak hardness that is found in the material, that is surface composite, it was around 66.9 HV in the nugget zone. So we can just see the trend of micro hardness. So obviously within the nugget zone, that is exactly at the middle part, the micro hardness is very much higher, and it reached around 66.9 HV. And in the TMA zone, because of the elongation of grains, the hardness was much limited. And in the base material zone, it had an average hardness of 57.9 HV. Yeah. And the hardening mechanism is in terms of surface composite could be elaborated based on dispersion strengthening phenomenon. So generally speaking, this interface between the solid phases determine this dispersion strengthening effect in composites or even in alloys. So we have coherent interface coherent with strain, semi-coherent, and incoherent interfaces. And a coherent interface is one that has perfect registry of lattices right from material A and material B. If there is a perfect registry of lattices, then they are called as coherent interface. If there is a small strain with respect to material A and material B, then they are called as coherent with strain. So there will be some strain with the interface due to imperfect matching. So the strain energy increases with the size of the growing particle, and there is a transition to a semi-coherent interface too. And if we have more amount of dislocations coming into the picture, then it will be considered as a semi-coherent interface when there is little matching of the lattices. If there is no perfect match of lattices at all, then they are called as incoherent interfaces. Most of the composites will have incoherent interface only. Why? Because we introduce ceramic phases into the metal matrix. So ceramic phases, their lattice will be completely different from that of the metals lattice point, right? So generally, this composites will have incoherent interfaces. So there is no matching of interface at all. So how do we get strengthening effect? So that is explained based on the concept of Friedel effect and Ormond mechanism. So when we have fine dispersion of insoluble hard particles, which is less than 0.1 micrometer, that will increase the elastic limit, and that will enable flow pattern of stress deformation, and that will lead to rapid hardening. Excuse me. Yes. So there are many factors that influence the dispersion strengthening of materials. First is the size, second is the morphology, third is the concentration, and fourth is the physical characteristics. And the dispersion strengthening to Friedel effect is very much limited. Why? Because only if we have a coherent precipitate, we will have a Friedel effect of dispersion strengthening. And if we have a big hard incoherent precipitate, that relates to Ormond mechanism. What happens in this Ormond mechanism is there will be a dislocation. If a material is subjected to stresses, there will be strain, so that will induce dislocation. So that dislocation continues to bend around this hard incoherent particle, and then it will just move on with the dislocation ring around the particle. Why? Because this dislocation is, it is difficult for dislocation to overcome the phase boundary between the host lattice and the incoherent particle over there. So that is why we have enhanced hardness in the composites, that is reinforced with nano phase reinforcement particles of alumina, which is a ceramic phase. And coming towards corrosion analysis, so first we have done some basic immersion corrosion test too. In this basic immersion test, what we have done is we have taken the specimen, the surface composite specimen, we have immersed it under simulated body fluid. Okay, so the simulated body fluid is made of, there are many types of simulated body fluids available in the open market. So first is Hank solution, that is what people generally use, and we have used Delbaco's phosphate buffered solution, and that is advantageous. Why? Because that has some sort of stabilizing agents for maintaining the pH 2. And how it is done is we have made a thermostatic water bath of that can maintain temperatures of 37 plus or minus 0.1 degrees Celsius for a period of 7 days, and we have monitored the pH with a pH meter with a sensitivity of 0.01. Okay, and we have just immersed the specimen into that container containing SBF. We place that container in thermostatic water bath that has temperature of 37 plus or minus 0.1 degrees Celsius. So that mimics the human body environment. And after a period of 24 hours, we have taken the specimen out, we have dried it, we have cleaned it using chromic acid, that is prepared by 100 gram of chromium oxide in 1000 ml of distilled water. Then we have taken the corrosion rate of these specimens. So this was done in triplicates at an interval of 24 hours for a period of 168 hours. That means we have done for 7 days the same steps. Okay, and based on our analysis, so here's the result of corrosion rate after 3 days and 7 days of immersion. So after 3 days, the base material had a corrosion rate of 4.7 mm per year, and the corrosion rate of the composite that we have fabricated is around 0.337 mm per year. the corrosion rate after 7 days came down as 1.05 mm per year in terms of in base material, and it came down around 0.287 mm per year in the composite. And when we have analyzed the surface morphology, the cracks were mini and narrow after 3 days of immersion in base material, and in terms of composite it was few and narrow, and after 7 days there is obviously propagation and widening of the cracks, and that is all because of the corrosion reaction that is taking place in the material. And coming towards the distribution of corrosion products, in AZ91D, the corrosion products distribution was highly random and it was scattered. But in case of the composite, the corrosion product was uniform. It means there is a complete layer of formation of corrosion products. And the structure was branched one in base material and clustered one in AZ91D aluminum composite too. So here we could see how the corrosion products are distributed and how crack has propagated over a period of 3 days and 7 days in the base material and the composite. Yes, coming towards analysis, we have done EDS and XRD analysis to confirm the presence of corrosion products and the composition of corrosion products too. So the initial analysis was EDS analysis. So from this we came to a conclusion that the corrosion product consisted of magnesium, aluminum, oxygen, calcium, sodium, chlorine, potassium, and phosphorus. So these are the major elements in the corrosion products. So the major parameter when we have to analyze when we subject a material to simulated body fluid is the calcium to phosphorus ratio. Why? Because the calcium to phosphorus ratio will give us an idea about the formation of hydroxyapatite crystals in the corrosion product. If there is a formation of calcium hydroxyapatite crystals, that confirms that the material will have a good biocompatibility. Why? Because this hydroxyapatite is a very good biocompatible compound. Why? Because this is the inherent material that is present in the bone itself. Okay, and we have done elemental mapping analysis that also confirms the overlapping of calcium and phosphorus, which confirms there is a possibility for the formation of calcium phosphorus salts, calcium phosphorus based salts. And XRD analysis also confirms the presence of hydroxyapatite based crystals. So the small peak that is between 20 to 30 degree corresponds to HAP. So that was confirmed through XRD analysis too. So here is the phenomenon that is taking place in the material. So once we subject a material towards a simulated body fluid condition, what happens is there will be formation of magnesium oxide or magnesium hydroxide because it is in aqueous environment. This magnesium hydroxide is highly unstable. So what happens is this readily reacts with the chloride ions to form magnesium chloride, and this magnesium chloride has high dissolution rate within the solution. So what happens is there will be new exposure of materials with respect to time. So that will lead to, yes, just give me a second. Yeah, so the dissolution of magnesium ions and formation of magnesium hydroxide is the first step, and it will act as a potential barrier to absorb calcium and phosphorus initially. But what happens is there will be formation of magnesium chloride that will create more corrosion sites by dissolution. Okay, and that will lead to interaction of calcium and phosphorus that is present in the simulated body fluid to interact with magnesium to form salts or corrosion products related to calcium and phosphorus based ones. And what happens is there is more accessibility of magnesium ions to phosphate ions. So that results in the formation of flower-like clusters. So those flower-like clusters are nothing but magnesium, calcium magnesium phosphate layer or calcium hydroxyapatite layer. That formation of adherent layer of corrosion product decrease the corrosion rate in material. So initially we had high corrosion rate, then there is reduction in corrosion rate. So that is all because of this formation of hydroxyapatite. So if there is a formation of hydroxyapatite, it is obvious that the material is biocompatible. Since we have bring down the corrosion rate to less than 0.5 mm per year, so this is also a good sign for the material to be an effective biodegradable implant. Yes. And coming towards the electrochemical corrosion analysis. So in this we have done potentiodynamic polarization concept only. The electrolyte used was synthetic body fluid based on Delbecque's phosphate buffered solution. The potentiodynamic polarization plots are just shown over here. So the red colored line indicates the potentiodynamic polarization plot of the base material, and the blue colored line shows the potentiodynamic polarization plot of the prepared surface composite. So from this we can observe that the corrosion potential of the base material was more noble or more than that of the fabricated surface composite. But the corrosion rate, coming towards the corrosion rate, the specimen had the surface composite had very low corrosion rate than that of the base material. So we have to analyze this thing in detail. So we have gone for AFM analysis too. And even before that, let me clarify the cathodic and anodic kinetics. So the electrochemical corrosion rate, I mean, analysis gives given us an idea that there is analogous cathodic kinetics. That is, there is minor influence of nanophase nanophase alumina particles over the corrosion phenomenon of the material. However, there is unique anodic dissolution characteristics. So we can obviously see if the corrosion potential is increased beyond the corrosion potential, there is an exponential increase in current in case of AZ91D, that is the base material. So that resulted in high dissolution rate of magnesium from the material. But in the case of composite, we can see a pseudo passivation tendency. So there is a pseudo passivation tendency. Why? Because there is limited current after corrosion potential. So we can confirm that there is partially protective corrosion product films that is forming right from minus 1.38 volt and minus 1.260 volt. So that resulted in enhanced corrosion resistance of the surface composite. Added to that, if the corrosion if the potential is increased beyond this minus 1.260 volt, that is the breakdown potential, beyond which the surface composite is also subjected to high corrosion rate. But within this region of interest, we have very low corrosion rate. And coming towards the corrosion current and corrosion rate of the specimens, from the electrochemical analysis, the base material's corrosion rate was around 4.49 mm per year, and that of the composite was around 0.25 mm per year. So from this, we can conclude that the corrosion rate that is determined from immersion corrosion rate and immersion corrosion rate is same, and it is equal to that of the electrochemical corrosion based corrosion analysis. Yes, and coming towards the ductility or the corrosion rate of the materials, the corrosion potential of the base material was 0.018 volt, noble than that of the surface composite. However, the corrosion rate is 14.78 times lesser than that of the base material. So that is a complete contradiction. So that could be explained on the basis of intrinsic electrochemical behavior of the material, which is influenced by the electron work function. So this electron work function is the minimum energy required to extract the electron from the subsurface without kinetic energy. And if we have a low material with low EWF, electron work function, there is high tendency for the electrons to take part in electron reactions or chemical reaction. But in case of this composite, we have finely dispersed alumina on the surface. This alumina is a ceramic, so it has a very high electron work function, which means that the tendency for the electrons to take part in electrochemical reactions is very low. So this has retarded the anodic dissolution rate of magnesium 2. So here is the surface potential map that is obtained from AFM, atomic force microscopy technique. This we have used Kelvin probe microscopy for determining the surface potential. So X and Y axis gives us the distance and Z axis gives the surface potential of the material. So obviously we can see the surface potential was somewhat higher in terms of nanophase alumina dispersion. So the corrosion rate of this composite is lower than that of the magnesium alloy AZ91D. And these are the brief outcomes of the research. We have fabricated a composite by dispersing nanophase alumina on the surface of AZ91D by friction stir processing. The nanophase alumina particles nucleated magnesium grains during recrystallization, and it restricted the growth of recrystallized magnesium grains. And that resulted in grain refinement. Added to that, friction stir processing has fragmented and uniformly dispersed the beta phase. So this cumulative effect and the homogeneous dispersion of particles resulted in high hardness in this chip zone, and homogeneous dispersion of nanophase alumina that has high electron work function increases the corrosion resistance of material too. Added to that, the surface composites had an adherent layer of calcium magnesium phosphate or calcium hydroxyapatite in simulated body fluids that resulted in decreased corrosion rate. And previous studies have also confirmed that if there is formation of such compounds, that will enhance osteoconductivity and it will support bone growth. So from this, we can conclude that magnesium alloy that is reinforced with nanophase alumina is going to be biodegradable and effective biodegradable implant. Yes. Thank you for your patient listening. So if you have any doubts or queries, please go ahead.
Any questions from the participants? The Sitaraman sir is asking in the chat, why corrosion is a bliss? Hello? Hello, Vignesh sir?
Yes,
Yeah. Yeah,
yes,
I'm
yes,
audible,
ma'am.
right? So Sitaraman sir, Dr.
Yes,
Sitaraman
ma'am.
is asking why corrosion is a bliss.
Why corrosion? Yeah, fine, okay. So why? Because that is framed when I have started to work on biodegradable implants. So generally people think that corrosion is not good for materials, but in case of medicine, it is going to be a wonderful thing. Why? Because this will result in biodegradation of material in vitro itself, that is within the body itself. So that will avoid secondary revision surgery. So that is good for medicine based implant industries. So that is why I quoted corrosion is a bliss. Thank you for your question, sir.
Probably that was a little confusing because we never wish the material to corrode.
Yes.
Uh, any more questions from the participants? Sir, you are able to unmute yourself. Yes, you are able to unmute yourself. So you can please proceed to unmute and ask anyone. So, let's presume there are no more questions.
Sure. Okay, thank you.
There are no questions from the participants.
Okay, ma'am.
Okay. Sir, thank you very much for your time, sir.
Yes, thank you, ma'am. I thank MLR Institute for giving me an opportunity to present my research outcomes too. Yeah, thank you.
Yes. On behalf of Familiar Institute of Technology, Dr. Satyanarayan Gupta, sir, and Dr. K. Srinivas Rao, sir, entire team of Aeronautical Engineering, a big thank you for you to share your time, sir, and knowledge also.
Yes.
We look forward for future collaborations too. Thank you very much,
Of course,
sir.
of course. Thank you, ma'am. Thank you for your
Yes, sir. For the information of the participants, the feedback link has been posted for both the sessions in the chat window. You may please post the feedback. And the next session will be from tomorrow. And we have the hands-on session. Few of the participants were asking regarding the hands-on session. The last 3 days we'll be having 1.5 hour each, a hands-on session. So please kindly be prepared with the installing of the software. Answer student version is available online, which is free. You may use your institute mail ID for the same, so that you can log into it. Madhusudan sir, you're silent today actually. So the link will be open for another 5 minutes, the meeting, not 5 minutes, 2 minutes. You can just fill up those who have just joined. Session 1 and session 2 both are available in the chat window. You can just search for session 1 and fill both the forms.
Madam, that feedback is only session 1, madam. Session 2 only session. Both sessions in only one feedback, madam. Only one form, one Google form is there, madam. That is both for both sessions, sir.
So you are there in the WhatsApp group, sir?
Yes, madam.
Okay, I have posted the session 1 feedback in the WhatsApp group. Session 2 also I'll be posting now. Now it's in the chat window. So you can access from there.
In chat window, we have only session 2 form, madam.
So session 1 also is there. I think you logged in late. Let me just provide you with the session 1 feedback.
Okay, madam.
I'll just get back. This is session 1, sir.
Thank you, madam.
Yeah, I provided it even in the WhatsApp group also.
Okay, madam.
And I sincerely thank that you people are not forwarding it to anyone. I'm just getting the number of responses are also limited.
Yeah, madam.
Yeah. Usually what happens is they forward and I get 200, 300 responses.
Yes, sir.
Participants are 40 and 200 responses will be there. But that's not happening.
Yes,
Thank you very much for your cooperation.
Thank you, madam.
tomorrow we'll be meeting at Uday sir, session 2 da sir. Okay. 9:45, and please install answers in your systems and make space for it. We are having hands-on session from 17, 18, 19, the last 3 days. So we are closing the meeting now. I hope everyone has filled. I did not ask who is the speaker and all these sort of questions. So thank you, Nagraj sir, Madhvi ma'am, Sabrika sir, and all the participants for the time and the continuous encouragement for the past 8 days. We have still 4 more days to go. Let's all meet tomorrow at 9:45 sharp. Thank you very much.
Thank you, madam.
Thank you. I'm closing the meeting, sir.
Yes, madam.